this is the break time. It is always difficult for me to gather back these mental break things. Let us share some logic, right? Hopefully you would love it, right? But not do it. You will love it, but not do it. The more you learn, the more you know, right? So this is a standard, isn't it? That you go through this course and that course and this, the first week, the second week, the third week. The more you learn, the more you know. So this is good. But the more you know, the more you forget. Yes or no? I mean, whenever I ask you that, did you cover this in material science? You want to say, no, we did not. And sometimes you even forget that you did material science with me. But that is what, right? And we joke sometimes that what is this habit of formatting your hard disk? You did a whole course and now you are saying that we don't remember anything. But yes, if you learn a lot, then you forget a lot also. You have to revise it and so on. So the more you learn, the more you know. The more you know, the more you forget. But now the logic. The more you forget, the less you know. Again, right? Very logical. So now the sequence, the more you learn, the more you know. But the more you know, the more you forget. And the more you forget, the less you know. So logical conclusion, why learn? Right? So whenever you don't want to study, you have the logic now. Back to void nucleation. So in the first sentence, we were telling you the basics which we explained in the previous slide. A void forms around a second phase particle or an impurity inclusion when sufficient stress is applied to break the interfacial bonds between the impurity particle and the base matrix material. There are a number of models for void nucleation. The most widely used continuum model for void nucleation is by Argonne and others. This all, if you remember, is a short form for all others in the Latin language and so on. And this argon is not a gas, this is a person. Now here there is one more word, continuum. We have again mentioned it earlier that all the mechanics that you study in general, from basic level to master's level to PhD level and so on, assumes that the material is a continuum. The material is a continuum. Remember your crystal theory. At the crystal level, in every BCC or FCC and so on, there are atoms. But the two basic crystal theory postulates on which everything was based was that each atom is a solid round sphere and all atoms in a unit cell touch each other. So there is a continuum. The material does not have gaps. There is a continuum, right? So that is why the higher level mechanics of material is called continuum mechanics, right? That is what you are not doing continuum mechanics here, but if you do a master's degree in mechanical engineering, most probably, then one of the basic master's level courses that is available is continuum mechanics. And especially if you want to be in the applied mechanics area of mechanical, not the thermodynamics and thermofluids area, not the dynamics and control area. If you want to be in the applied mechanics area of mechanical engineering, then continuum mechanics generally becomes a core master's course. But okay. So one model by Argonne and others, the team of Argonne, it uses a continuum model for void nucleation. Interfacial stresses at a cylindrical particle, interfacial stress at a cylindrical particle is approximately equal to the sum of the mean hydrostatic stress and the effective von Mises stress. Again, remember now, you go back to your solid mechanics or machine design where you know these words. The mean stress, you know, there are, if you go to your solid mechanics, there are three principal stresses. sigma 1, sigma 2, sigma 3, principal stresses. We are not talking of sigma x, sigma y, sigma z. Remember, sigma x, sigma y, sigma z is just your coordinate system, x, y, z coordinate system. So you measure the stresses along x, y, z. But if you go deep into the solid mechanics, then there are three principal stresses, and those directions are 1, 2, and 3. So the three are sigma 1, sigma 2, sigma 3. So the three principal stresses are there. If you take the average of them, it is called the mean stress. It is also called the hydrostatic stress. The word hydrostatic, if you remember, is coming from that if you have a fluid, liquid or gas, right? If there is, a pipe in which water is flowing, so then the pressure of the pipe is the same in all directions. You go upwards, you go to the right, you go towards the bottom, every side it is the same. So any stress which is equal in all directions, therefore, is called hydrostatic in nature. Hydrostatic means in the fluid state and so on, right? So it is just a name. It is a mean stress, mean of the three principal stresses. But it is called hydrostatic because this mean stress, once you have taken the mean, you are assuming that this mean stress is there in every direction. And then if you remember your solid mechanics, or if your teachers told you about it, especially if you did an elective course and so on in finite elements and so on, there we always tell you that there is an effective stress which is called the von Mises stress. So you don't have to remember it, we are trying to explain it to you again. Now, decohesion, remember, there is a cohesion, there is interfacial bond between the particle and the matrix material. Decohesion, when this bond between the impurity particle and the base material breaks. So decohesion stress is defined as a critical combination of these two stresses, these two. That sigma critical is sigma E plus sigma M. Sigma M is the mean stress and sigma E is the effective von Mises stress. Von Mises is one of the pioneers of the applied mechanics area, especially in stresses and so on. So the effective stress is given the name of von Mises stress. So the critical stress needed for decohesion is this. Now we are reminding you this simple definition that the effective of or von Mises stress, sigma E, is 1 upon root 2, right? And then the root of this whole thing raised to half. Sigma 1 minus sigma 2 square, sigma 1 minus sigma 3 whole square, sigma 3 minus sigma 2 whole square. So sigma 1, sigma 2, sigma 3 are the three principal stresses, right? And it is a difference of the three terms. Difference between 1 and 2, between 1 and 3, between 3 and 2. Because you are squaring it, so it does not matter whether you write sigma 1 minus sigma 2 or you write sigma 2 minus sigma 1, it is a square of this. So if you remember, what is the basis of finding this? In all physics, you know the root mean square, RMS value. In wave theory, here, root mean square. Why? Some differences are plus, some differences are minus. So if you just add the differences, then the plus and the minus may cancel out each other and you don't get the true difference. If you square the difference, there is some difference which was positive, you square it. Some difference which was negative, you square it. Now all of them are positive and then you take the root of it. So this tells you the real difference, right? So root mean square. So if you see exactly, this is the root mean square type of thing. That you are taking the differences between sigma 1, sigma 2, sigma 1, sigma 3, sigma 3, sigma 2. The differences. You are squaring them and adding them together. But now you are taking the square root of it. So this is one way of doing the root mean square. This is not exactly root mean square, but the method that if you want to find, right? So this is called the effective von Mises stress. And of course, the mean stress, as I told you, is simply the mean stress. These are the three principal stresses, sigma 1, sigma 2, sigma 3. The average of them is the mean stress. And sigma 1, 2, 3 are the principal normal stresses, right? So though you know it from earlier, but even if you did not, we have now defined what is the mean stress and what is the von Mises stress. The mean stress is the average of the three principal stresses. The von Mises stress is the effective value that at any point in the material, what effective stress will the material feel, right? Then it is that. Now, Bremen Research Group in France, it was a company, a research group in France, applied the argon criterion to experimental data for a carbon manganese steel. Steel are thousands of types because every percentage change in carbon makes a different steel, and then you add manganese or sulfur or phosphorus or whatever to it more. So carbon manganese steel, this is one of the more used steels. So this argon group applied the this Bremen group applied the argon theory to this type of steel experimentally. Semi-empirical relationship. You see, when we derive a mathematical relationship, it is called modeling, right? That a physical thing is happening, you are studying it. Can you give me an equation for it? Because once the equation is there, then I can predict for the future that if I change this slightly, what will happen and so on. As long as you do only experimentally, then you can tell only for this material under the current conditions. But if you make a mathematical model, so that is mathematical modeling, right? In mathematical modeling, you can have the equation purely by theoretical understanding based on the physics or the mechanics of the material. So then that model is called an analytical model. On the other extreme, right, you can do pure experiment and then try to do curve fitting based on statistics. That is called regression. So that is a regression model. That is a regression model. You call it a statistical modeling, you call it a stochastic modeling. So on one side, there is analytical modeling. You go into the physics of the material and you derive the model or the equation purely based on the theory. On the other extreme, you perform a lot of experiments, repeat that experiment many times by changing small parameters, and then try to do curve fitting, regression analysis in statistics, and you get a model. So these are two techniques, right? Analytical model, statistical model. Then you have done the course on numerical analysis. You divide the whole area into small fractions, and for each small fraction you apply linear theory and then combine them for a numerical solution. So now you can have an equation for the same process which is numerically. So it is a numerical model. When you combine experimental and purely theoretical, then we call it semi-empirical. Empirical means experiment based and analytical means theory based. Semi-empirical is a combination of the two. So this group did this. They applied the argon criterion, did the experiments on carbon manganese steel, and came up with the semi-empirical relationship for void nucleation at the manganese sulfur inclusions. That the inclusion point, the impurity points are manganese sulfide. The manganese sulfide point here in the iron. So critical is mean plus C times sigma E minus sigma YS. You know, this is the yield strength. This is the von Mises equivalent stress. This is the mean. So mean stress and von Mises stress, these are based on sigma 1, 2, 3 and yield strength of the material. And this C is an experimental parameter. So this is a fitting parameter, right? A regression based type of thing. So this is a semi-empirical relationship based on a lot of experiments. And this C is about 1.6 for longitudinal loading. If you apply load along the axis of the material, and this C is approximately 0.6 for transverse loading to the rolling direction. If you are performing the rolling operation, but the loads are in transverse direction, then the value is 0.6. So this is, again, the derivation is not there, but the equation based on semi-empirical model is there now for ductile fracture.